Imagine being able to see through clouds, rain, or even darkness. That's the power of synthetic aperture radar, or SAR. SAR is a remote sensing technology that uses radar waves to create images of the Earth's surface. Unlike traditional cameras that rely on visible light, SAR systems emit their own microwave pulses and measure the reflected signals. This allows them to operate day and night regardless of weather conditions. However, SAR images are typically presented in grayscale, which can make it difficult to interpret certain features. SAR images appear in grayscale because they represent the intensity of the reflected radar signals. Brighter areas indicate stronger reflections, while darker areas represent weaker reflections. This information is valuable for various applications, such as mapping terrain, monitoring crops, and detecting changes in the environment. However, the lack of color can limit the amount of information that can be extracted from these images. For example, it can be difficult to distinguish between different types of vegetation, or to identify man-made structures based on grayscale values alone. Generative adversarial networks, or GANs, are a powerful class of deep learning algorithms that have gained significant attention in recent years. GANs consist of two main components, a generator and a discriminator. The generator is trained to create realistic-looking data, such as images from random noise. The discriminator, on the other hand, is trained to distinguish between real data and the fake data generated by the generator. These two networks are trained in an adversarial manner. The generator tries to fool the discriminator by producing increasingly realistic data, while the discriminator tries to improve its ability to detect the fake data. This adversarial training process continues until the generator produces data that is indistinguishable from real data. GANs have shown remarkable results in various applications, including image generation, style transfer, and image-to-image translation. GANs offer a promising solution to the challenge of colorizing SAR images. By training a GAN on a dataset of paired SAR and optical images, it is possible to teach the generator to predict the colors that would be present in a corresponding optical image based on the input SAR image. This process involves feeding the generator with grayscale SAR images and training it to produce colorized versions that resemble real-world optical images. The training process relies on loss functions to guide the generator and discriminator towards their respective goals. The L2 loss, also known as the mean squared error, measures the pixel-wise difference between the generated colorized image and the corresponding real optical image. This encourages the generator to produce images that are visually similar to the real ones. Additionally, adversarial loss is used to encourage the generator to produce images that can fool the discriminator, further enhancing the realism of the generated colors. Colorized SAR images have the potential to revolutionize various fields, including disaster management and urban planning. In disaster response scenarios, colorized SAR images can help first responders to quickly assess the extent of damage, identify affected areas, and plan rescue operations more effectively. For instance, colorized images can help distinguish between flooded areas and dry land, making it easier to identify areas in need of immediate assistance. In urban planning, colorized SAR images can provide valuable insights into land use, infrastructure development, and environmental monitoring. By combining the all-weather capabilities of SAR with the visual richness of color, urban planners can better understand the spatial distribution of different land cover types, such as buildings, roads, vegetation, and water bodies. This information is crucial for making informed decisions about urban development, transportation planning, and environmental protection.